while since you've seen my kitty friend. Say hi to everyone. Hi. Now I'm going to go away. So today what I'm going to do is I'm going to talk to you about Gibbs free energy. And so what is Gibbs free energy? Well, it determines whether or not a reaction goes or doesn't go. And to understand this a little more fully, let's backtrack. So haven't we said in the past that exothermic reactions, those are, they're pretty good. They make reactions want to go. In fact, every reaction wants to be exothermic. They want to lose energy. Conversely, reactions don't want to be endothermic. They don't want to gain energy, which begs the question, why would any reaction ever go if it was endothermic? And if energy was the only consideration in whether or not a reaction went or not, then endothermic reactions wouldn't go. But there's another thing, and it's called entropy. And entropy we just discussed in the last video, and entropy is simply disorder. And reactions love disorder. So if you give a reaction more disorder, that's good. If you take away disorder, that's bad. So it's going to kind of be an evening out between the two of them. Now, if you offer a reaction exothermicness, if that's a word, in other words, you want its change in enthalpy to be negative, that's a thumbs up. If you then say that reaction, I'm also going to give you more disorder, that's another thumbs up. And if enthalpy and entropy are both thumbs up, that reaction will go always. We say the reaction is spontaneous or thermodynamically favorable. Conversely, if a reaction is endothermic, which means that it is a positive change in enthalpy, that's bad. And if the reaction ends up being less disordered, that's also bad. That reaction will never ever go. The tricky part is what happens if one of the two, enthalpy and entropy, because remember, those are the only two things that determine whether or not a reaction will go. What if one is good and one is bad? So let's say we have an exothermic reaction, but the reaction has less disorder. Or if we have an endothermic reaction, but the reaction has more disorder. Well, that's where Gibbs free energy comes in, and there is a kicker that determines whether or not one or the other will work, and that happens to be temperature. So a kicker, by the way, if those of you who are not a gambling folk, which I'm hoping that most of you guys aren't, is if you have the same car, the same pair as someone else. Let's say you both have a pair of twos, and your opponent has a king and you have a 3 as your highest card, which I don't know how that would work exactly, but let's say that was the case, you lose. So how does that play out in chemistry world? Well, we deal with something called Gibbs free energy. So Gibbs free energy is known by this equation. And I want you to take a look at this equation, and I want you to see if you can recognize that there is change in H in here and there's change in S in here. Both of these two expressions, I don't know why it's disappearing as soon as I write. Let me try and change the color here just because. Like the color is going to change, right? So these two things right here, both of them, I do not know why they're disappearing. That's really, really weird. So these are the two characteristics that we care about. Now, it should be noted here that our change in enthalpy, we really like our change in enthalpy to be negative, don't we? And we really like our change in entropy to be positive, right? Now, if you take a look here, isn't the T attached on to this change in S? So whatever happens to the T is also going to impact the S because they're tied in this little in this expression. You should also be aware here that the temperature is always in Kelvin, and that's a big deal because Kelvin, you cannot have a negative value. 0 Kelvin is the lowest you can go. If it was Celsius, let's say you have a negative 53 degrees Celsius, that's problematic because see this negative here? That's going to mess with our signage over here, and signs matter, and here's why. Change in G, or the change in Gibbs free energy, it determines whether or not a reaction is spontaneous or not. Now, when I remember I said spontaneous is also known now as thermodynamically unfavorable or thermodynamically favorable. I didn't want to write the whole thing out. That's favorable. Well, the sign determines that. So if our change in G is negative, we're going to have a spontaneous reaction. So we like to have a negative change in G. If our change in G is positive, then the reaction is not going to work. It's non-spontaneous under any conditions. If our change in G is 0, then we are at equilibrium. And we've just got through a whole unit on talking about equilibrium, so this kind of makes sense. You should also be aware that the change in G, if you have a reaction going one direction and then you push the reaction in the other direction, the reaction in the opposite direction's change in G will be the reverse of what the change in G was going forwards. Now, what you should be also aware of is that if the reaction is spontaneous, if it goes one way, it will not go the other way. So change in G being negative means that you will always be spontaneous. Now, let's take a closer look at this because it can be a little bit tricky to understand what happens if one condition is good or bad. So I'm gonna write this in here, the change in G expression, and is change in H minus T change in S. And I'm gonna give you some scenarios here. And I'm gonna put the degrees in right now because we're under standard conditions. So I'm gonna give you a few scenarios and we'll just call them scenarios. I'm just gonna write scene 1. And so scenario number 1 is this. We have an exothermic reaction and we have more disorder. Now, just in case you're wondering here, exothermic means that our change in enthalpy for the reaction is negative. And that's pretty good. More disorder means that our change in entropy for the reaction is positive, and that's also good. So I can, without even looking at our equation, I can tell you that this reaction is going to go. But let's do the mathematics on this because it's kind of helpful to see how this all fits together. So if we go over here and we write, all right, our change in enthalpy is negative, and we're going to subtract, and in this case our entropy is positive, and remember that our T can never be negative. Wouldn't that be a negative subtracting a positive? And if that was the case, every single time, wouldn't this reaction be negative or spontaneous? Again, I'm rebelliously keeping on saying spontaneous instead of thermodynamically favorable, but they are the same things. What if I go the opposite route? What if I tell you scenario number 2 that I have an endothermic reaction and I have less disorder? So essentially, this is a poop sandwich. No one wants this. You have your change in enthalpy. Okay, that's really dumb. Just realize that. Your change in enthalpy is positive and your change in entropy is negative, and both those things are bad. So let's come back over here. We'll use different colors to vary up each one. That means our enthalpy is positive, and that's no good. And we're going to subtract our entropy, and our entropy is negative, which is also no good. So if you have a positive, subtract a negative, isn't that going to give you a positive every single time? And wouldn't that be non-spontaneous or non-spontaneous, we like to call it in the business? Where it gets tricky is what happens if you have one good characteristic and one bad characteristic. There's no such thing as good and bad, but just say that's the case. So let's say I have my reaction is exothermic, and my reaction is also has less disorder. Now, I want to point out something to you. We don't have a ton of room here, but let me just scroll up a little bit here, if I can. It does not want to work for me here. Okay, I'm going to do this right here, just so we have a little bit of room. So, if I look at my expression right down here, which is T change in S, you understand that whatever you do to T will impact our S because they're multiplied by each other. So if I raise my T, wouldn't that mean that this entire, not that the S will raise, but wouldn't this entire expression go up and become more important? So if we raise the temperature, then our entropy expression becomes more important. If we do the opposite with our T change in S and we lower our temperature, that means that this expression becomes less important. Now remember, there's always a battle. There's a teeter-totter. And on one side of the teeter-totter, we have change in enthalpy. And on the other side of the teeter-totter, we have change in entropy if they are opposite each other. And the question is, what's going to sit on this side with the temperature? If you have a huge T on this side, then it's going to tilt in this direction, and entropy is going to determine whether or not it's good or bad. It'll determine whether or not the reaction goes. Conversely, if we make this a really, really tiny T, let's pretend that this didn't exist, right? If I make a really, really tiny T, well, that's going to multiply by this change in S, and it's going to make this entire expression really tiny, and it's going to tilt in this direction. So let's go back to the problem we were just doing here. And I have an exothermic reaction, and I'm going to change colors again just so you can see, we're doing something different. So we have an exothermic reaction, and we're going to agree that that is A-OK, right? And we have less disorder, which is not great. So if we take a look, we have a negative, and we're subtracting a negative. So if you kind of broke this apart, essentially on this side we have a negative, and this side we have a positive. Whatever side is bigger will win. Well, let's say that enthalpy and entropy are whatever they are. They've given us two numbers. It does not matter what those numbers are. They'll often ask in a problem, under what conditions will this reaction go? And will you agree with me that temperature can be raised or lower? So they'll say, under what conditions will this reaction go? Well, would you agree with me that in this case, my entropy is bad? It's going to be poor. It's not going to make the reaction go, and our enthalpy is good. So if my entropy is bad and our temperature is attached to it, wouldn't we want to lower the temperature in order for the reaction to go? So we'd say this: under conditions of lower temperature, the reaction is spontaneous. If we were to jack up the temperature, then this expression would become more and more important, and the reaction would become unspontaneous. So in this case here, and under low temperature, this is only under low temperature, the reaction would be spontaneous. Under high temperature, it wouldn't be. Let's take a look if we were to go the opposite route. Let's say we have an endothermic reaction. And by the way, when I say endothermic, you do understand that I'm saying change in enthalpy is positive, right? And I have a more disordered reaction, which is really good for us. That means change in S is positive. Over here in our equation, we have a positive, and we are subtracting a positive. So if you break it down the center, on this side we have positive, on this side we have negative. But in this case, isn't our entropy good and our enthalpy is bad? So if we wanted the reaction to go, wouldn't we have to raise the temperature? Or, I mean, this is assuming we don't have numbers. We could actually figure out if we had a certain enthalpy or entropy and a certain enthalpy. You realize that this number S could be enormous. If I lower the temperature enough, I could still make this expression I'm circling here, I'm talking about this expression up here. But if I have a huge S, right, but then my temperature is incredibly low, that could still make this expression not greater than the other expression on the other side. But in this case here, we'd say under conditions of higher temperature, the reaction is spontaneous. So we could say it is spontaneous under conditions of high temperature. Now I've kind of put all this stuff together into a little chart here, and this is repeating kind of what I've said here. Under what conditions? Well, if we have a negative enthalpy and a positive entropy, it's spontaneous always. If you have a positive enthalpy, which is bad, and a negative entropy, which is also bad, you're non-spontaneous always, which is positive. But if you have a positive enthalpy, which is bad, and a positive entropy, which is good, if the temperature is high, it'll work. If you have a negative enthalpy, which is bad, and you have a negative enthalpy, which is good, and you have a negative entropy, which is bad, then if you lower the temperature, the reaction will work. So this expression here, if the temperature is very low, then the term T change in H isn't very significant compared to change in H. In that case, the change in enthalpy almost single-handedly determines how spontaneous the reaction is. These two statements right here are exactly what we were talking about before, because they'll ask you under what conditions will a reaction actually go if you have one of these two good and one of these two bad. So entropy and enthalpy are the two things that will determine whether a reaction will go, but temperature is the thing that balances it all off. Now, we normally would have to do a bunch of stuff here. See this expression here where we have change in G equals negative RT natural log in K, and change in G equals negative NT E. We definitely will not have to use this expression right here. This bottom one here we may have to use. They're giving us a conference call. Again, this is for just this year if you're watching it later on. We'll be determining whether or not they're going to require us to know this for the AP exam. Anyway, hopefully this has been helpful, and stay safe. Thanks. Bye.